but now we do change the point so we get like an arbitrary map from R2 to T phi S. So that looks almost like, I mean, it already looks pretty promising, because what it does is, for every point x and y in the open subset, we get a map that relates things on S with the tangent vectors there, with just normal vectors. So we can use that map to transfer things that live on S, namely tangent vectors, on S, and talk about them in terms of normal vectors with the help of, because that one is a bijection. So let's make that a little bit more precise. The problem, namely, is that for the functions here, everything was nice. We had like our chart. That was something living on D. Then we mapped to S, and our function was a map from S to R. So we could just like take the composition and we would be done. But now we have a bit of a problem, because this map here takes values in the tangent vectors, but these ones are the things that we want to describe in terms of these ones. So we have to kind of take the inverse, and that's so it's like the opposite direction, which makes things a little bit more difficult. So let's talk about that a little bit more in detail. So what we can do is, for every point that lives in S, and which lies in the image of the chart, we can represent it in the chart. We find x and y in D such that if you plug in x and y into phi, we get like our point S. And these ones are unique because phi is injective. And then define, and now we define a certain expression. I'll first write it down and then walk you through. So it's a certain expression that depends on the point S. And what we do is we take the derivative of phi, which is like the map over there. And that one eats tangent vectors in R2. So what we do is we plug in our vector field, which we think on X, on D, which we think as a vector field, the constant one. And if you unravel the definition of what this one was defined in terms of that, that is nothing else than taking the partial derivative of phi in x direction, essentially that's this one, and then we have to keep track of the point, the x phi. And now we remember that x and y was essentially defined as the inverse of S. So what we get in total is that this one is dx evaluated of down here. That is d phi in x direction also evaluated at that point. So first of all, let me walk you through the definition again. So like this one is a map that eats vectors and gives you a vector at the tangent vector, at the tangent space of S. So this expression here is a tangent vector at phi of x and y in S. So that's phi of x of S is the same thing as Ts of S. So it's like it gives you for every S, you get like some tangent vector. And that tangent vector is defined to be we take the partial derivative of the chart in x direction, and then we have to say at which point we take the partial derivative, and the point is essentially the inverse image of the S that we plugged in. So that's like the mathematical formulation of that, but maybe it's like better to think of that as like a picture. So what we have, this one in the plane, it's just R2, it's just like dx. It's like the vector field that points in x direction. And phi is the map that makes like this like open subset into something curved, like this. And then if you do that, now curve it, but like look at what happens to the vector field. So we get like the same vector field, but just like now in the curved space. And that's exactly this expression here. Is, dx with respect to phi is essentially this one, that we keep track of the x, but we don't think of it as like a vector field in the plane, but really as a vector field painted on the surface, and the painting is given by the chart that gives us the coordinates, or like that says like how much you have to curl in this open subset into like this curved surface. So that's how you should think about this dx and d phi are the vector fields that go in the x direction, but like just like twisted by this chart that like gives you certain coordinates. And the cool thing is that what we get now is for every S, we get a tangent vector at that point. So that says that like this expression, which was defined dx phi, is actually a vector field on the surface. Description defines vector fields dx, phi, and dx, dy, and phi on S. So maybe just a look at like the picture again. That's like for open subset of R2. Then we have a map phi, which describes a large chunk of our surface. This one is phi of d. So it's actually only defined on points of phi of d. And what it is, it's like this picture is like we look at the vector field that goes in x direction. So that one would be dx, just the vector field. And then we essentially push it forward. It's actually also called push forward. So we transfer it with this map to a vector field that might change now. it's our vector field on that chart. And yeah. So we now define two canonical vector fields on phi of d, or like on the surface. So maybe it's good to have like a concrete example. So let's continue that example of the sphere. So there we have like the phi is already written there. So let's calculate what d phi in x direction is. So we need to specify a point on the sphere. So that's x, y, and z. X, y, and z is a point on the surface. And what we have to do is we have to calculate this expression here, dx, that point is given by d phi of x at x and y, where x and y is the point that maps to the s. So in our case, it's relatively simple because the point that maps to x, y, and z is just the x, y. So what we have is that we need to take the derivative of phi in the x direction at the point, and now it's just the point x and y, because the c is like determined by x and y. And we can do that. We have the formula up there, so you take the partial derivatives. The first one would be 1, the second one doesn't depend in x direction, and now we get 1 over x, the square root of 1 minus x. So that's the vector, and it really depends on x and y. So that's why I defined again on d or on that subset, because this expression is never 0 on the upper semi-sphere. So we have to say maybe a check that it's really like here I claimed that we get element of the tangent space of S. So far we only got like a vector. So let's double check that it's really a tangent space vector. And maybe the simplest way to see this is that we can write this also as 1 minus x, and then this expression downstairs here is just, we can express it again in terms of c. And now we have to say like check that 1, 0 minus x over c is a tangent vector at that point x, y, and z of the sphere. And we already calculated last time what this tangent vector was, or this vector space. This were all vectors v in R3 such that v times the point that we take is x, y, and z equals to 0. So it's all the orthogonal vectors. So what we have to check is that if we take the inner product that this one gives us 0. So let's do that. Like so what you see is that like this expression here just cancels exactly. So we indeed get 0, which is like what we wanted. So we get for every point x, y, and z on the sphere, we get a certain tangent vector. And the picture is as follows. Okay, that's more like an egg than a sphere, but I guess you get the idea. So this one is like like if I cut it like here, this one is the plane that is given by c equals to 0. And now we have a certain vector field that points in the x direction. So that we just think of like in the plane of as xy. That's our vector field that we just talked about at dx. And now the other vector field up there is like a vector field that's like defined on the sphere. So it's like defined on the upper hemisphere. And the point here is that if you project this vector downstairs, then you get exactly the green arrow in the x direction. So it's like you change the c direction, so it changes a little bit in the c direction, and it changes so that it's like tangent again to the sphere. But if you project it down, it's again like the one that points in the x direction. So that's what you see here is that this vector field here points, and if you project it down to the two first coordinates, it's just like 1, 0. It's like the vector field that points in the x direction. So that's this part. And like this second part here is in some way only there so that you can ensure that this inner product vanishes, so that this vector is really a vector that is tangent to the sphere. So you don't want something that points outwards. So if you have the sphere, of course, the vector field that just points in the x direction points outwards of the sphere normally. So you would like to kind of like turn that vector that points in the x direction, you turn it and make it like to be aligned with the surface. And that's like this part, the job of this phi here is to make sure that we have something that is pointing along the surface in the x direction. And then just x direction doesn't make much sense anymore. But like it says like, yeah, like what is the x direction under this curving? Like what is the x direction if you curve that? So that's so much to that example for the sphere. So let's go back to our objective. What we had was we wanted to actually express not like some strange vector fields on the sphere, but what we wanted to have some arbitrary vector field on the sphere, and we wanted to say like how that one can be represented as like something nice that lives on an open subset. So let's go back to that objective. So the first observation is that these vectors that we have two vectors, they are actually linear independent. They form a basis of the function space of TSS. So this one was two-dimensional, and now we found two particular vector which give you a basis. So that's again just a restatement of this fact because phi is non-degenerate. It's actually equivalent almost. Phi is non-degenerate means that like the Jacobian vectors were not parallel. If you look at like the definition of d phi x, they're essentially the Jacobian vectors. So we have two vectors now in S, and they form a basis. So that means that every tangent vector x, which is an element on that particular tangent space, can be written as a linear combination of these two vectors. Just some scalar numbers. And like these ones are not only like they exist, but they're actually unique also. So every vector can be represented now. If I have like a different, so I can do that with the y direction. So assuming I'm at that point here, I get like a second vector. So this one would be dy phi, and this one is dx. And if I have now some other vector that goes in some direction, then I can project it down onto the to the thing that goes in the blue direction, and then something in the green direction. And these projections are exactly these components V1 and V2 here. Now we have like almost done what we wanted to do, namely we managed to represent every vector in terms of two numbers, v1 and v2, using the chart. And so it makes sense to call v1 and v2 the chart representation. Phi. to be x of phi, which is in some way it's just the vector v1, v2. But again, it's maybe slightly simpler or slightly more comfortable to write this as dx and d1. So this one is the chart representation by definition of the tangent vector x. So what you do is like you have x, you find, or first of all you find like these two vector fields. There's d phi x and d phi y. So you find these two vector fields on S, and once you have that, every other vector can be represented in terms of two numbers. So you calculate these numbers that make it work, and then like these two numbers that you found, you write like again in terms of dx and dy to get like essentially a tangent vector on D. So you can think of that as, you want to think of that as tangent vector at D, which we identified with R2. So like this is this identification, right? Like here we think of that as just like a tangent, just as an ordinary vector in R2. And if you write it like this, then you think it a little bit more as like a tangent vector to D at some point. Okay, but that's the chart representation of a vector. So this one is of a particular point here. And so now if y is a, let's say x is a vector field, we don't not only have like one tangent vector, but like a whole collection of them at every point on S. Then chart representation of x is defined to be x of phi. So the point now is that it's like really a proper vector field on here. And the thing is that like we can do this strategy here for every point, for every vector, every tangent vector xs at ts, and then we get like v1 and v2, which now depend on the point. So v1 x1 where v1, which are now two functions on here, are given by the expression that x at a certain vector at a certain point is given as v1 x and y in terms of it's the notation maybe is the most confusing part about that. The idea is that every tangent vector, so if I fix a given point, I can represent that as a linear combination of these two vectors. And now I vary the points also and allow them to like be indexed by the chart. So we get like different points. So for every x and y, I get a certain phi xy, which is the like the deformed space coordinates. And at that point, I can evaluate my vector field to get some vector at that point in x. So that's it's a vector to the surface at that point. And because it's a vector at that point, I can represent it with respect to d phi x and d phi y given at that point. And these form a basis. And then, like v1 and v2, the numbers there in front of that, they of course depend on the x and y that I choose. If I choose different x and y, then I get different numbers. Maybe that's, again, a little bit more clear in the example. Maybe I do the example over here, because we have the sphere here. For example, the vector field is given by x, like capital X, and we look at like this vector field, and you can check that this one is indeed the vector field on S. So this one is an element of the tangent space. You just take like the inner product with x, y, and z, and then you see like by construction this like last term vanishes again. So that one is a vector field on S2. And we would like to say, like, what is now the chart representation of that vector field? So we would like to find this V1 and this V2. What you can do is that you can write this vector field as so that's essentially you just look at like these vector fields dx phi we calculated. It was like 1, 0, and then x over z with the minus sign. I think it's no longer on there. But then you see it's essentially this part. You just erase these parts where you have like just the x over here. That gives you the scalar multiple of the first factor. And similarly, if you take the derivative in the y direction, you get 0, 1, and then a certain expression down here. And that is like exactly c times the second vector. So that's just like looking at the expression that we got, like that this one was 1, 0, minus x over c. And then you see just like x times this term gives you these terms, and similarly for the y direction. So that gives you these numbers in front of the vector fields. So you have like these two numbers. For every point x, y, and z, we get like a certain number. That depends, of course, on the point. And then we read that off. So this is now this formula here of V1 and V2. Is now a vector field on D, and what we want, we can like think of that in like two ways. The first one is we just like write x and the b1 and b2, but we have to express each of these functions again as like in terms of the phi as a function of x and y. So can think of that. The first one is simple because it's the identity, but then we have to express c in terms of x and y, which would be a square root of 1 minus x squared minus y squared. So that's, if you think of that as like a vector, but perhaps it's a bit more convenient to write it like this. Maybe divided like in terms of dx and dy. So that gives you the chart representation of this vector field upstairs in terms of two functions, which are v1 and v2. So these are two functions on the open subset. Okay, I think it's time to go into a break. I understand that it's like, I think it's like the hardest part of the whole differential geometry course is like there's a lot of notation that like looks very strange. Like the ideas are very simple. Like the idea is like just like take that and curve it and like be done. So that's like the idea is very simple. The hard part is kind of like the notation that comes with that, and that's it's something that you just have to get used to. It's not something that is like super intuitive. And the hard part is also that a lot of differential, like books in differential geometry have different notations for all of that. So it's a little bit, like that's the hardest part in differential geometry in some way, is to get used to the notation and to make sense, like really to understand like what is going on. Like the ideas are relatively simple. It's just like, okay, you have a vector field there, you put it like forward, because like points are one-to-one correspondence, there's nothing like magically going on. But it's just like, that like if you want to calculate it with like concretely, then it gets a little bit tricky. So just like I understand it, it's hard. Just bear with me and like just like I try to just like also in the homeworks, I try to guide you a little bit to make it like easily calculable, so that you can calculate it and get a feeling for the notation. But yeah, I understand that it's not the most simple and like intuitive. But if you have any questions, use the break, I'm here. And then afterwards we continue in 15 minutes, which would be 45.
the directional derivative, so f just have to be smooth from the s to r.
Yes.
And so you can choose a lot of different f's.
Yes, so that works for like every arbitrary. Like it's similar to partial derivatives, where you say like, okay, like if I have some function that is given out of like two variables, x and y, and I can like take df dx and df dy. And it's similar here. It's like once you have like a function given, then you can take the derivatives in a certain direction. But like that, you also have to say like which directions you want to take. So that's why the capital X there.
Okay, I'm still confused why this can notify like the direction. So, and also if f can be chosen like freely, what's the, like you can have many different values.
Yeah, so
what's the meaning of the value?
Yeah, so f is like something that is given. For example, like in that example that I had with like the sphere, it's like a height function that says like how high are you on the sphere, for example. And then you say like, okay, like how does this height function changes if I'm on the sphere and I move like slightly. Like I'm at a certain point in the sphere, and like for example, if I then go along like something that is parallel to the equator, then so if I just like go on then the function is not changing at all because like the height is like the same. But if I go further up to the north pole there, then like the function changes slightly and gets like bigger. So and that's the thing that we want to calculate. It's like how much does the function changes if I change like the points in a certain way.
Okay. And what is this word mean? Like
canonical.
It doesn't mean like infinity or
like it means like something that is like what does it mean? It means that it's there without you need to choose anything. So like it's somewhere like in here it doesn't, it means just like say that you can maybe say natural.
Okay.
Natural would be maybe
okay. Thank you.